Okay, good afternoon. I'm going to give you a super short version of what we talked about in class today, or as short as I can get. First part was which part of the sliding block experiment required the most force and the least force. Most force was the carpet sandpaper combo. Least force was either the table and the smooth side of the block or the floor and the smooth side of the block. Depending on your group. Really what I wanted you to see there is that when we talk about friction, we're always talking about a pair, a system of two different surfaces that we're talking about. We never just talk about one surface and its friction. Second part, did you notice anything strange about when you were pulling on that? I'm going to get up close to the camera here. What you should see is that when you first pulled on it, it took more force, and then as soon as that object was in motion, it took less force. It went back down. Hopefully you noticed that, and hopefully you thought maybe that was a little bit odd. What that is you're measuring something called static friction. Overcoming static friction is getting that object into motion, getting it moving. Once it's got some momentum, now it's experiencing kinetic friction. Those are two different kinds of friction. Static friction is almost always going to be more than our kinetic friction. Okay, next up. You should probably copy down this slide here. The general idea is that the coefficient of friction, mu, I might sometimes write it like that. Mu is basically a rating of how much friction is present between two surfaces. So what you do is you pull an object, force of friction, that's how much force it requires to pull an object, and you divide it by its force of gravity. So how much force it takes to lift something up, to pull it up. When you divide those two, that should give you a mu, a coefficient of friction, or once again, a rating of how much friction is present. The idea being the smaller the top number is and the larger the bottom number is, algebraically, how those vary are going to affect the value of the coefficient of friction. Should stay constant. If you use more mass, it should give you more force of friction and more force of gravity, but it should give you the same coefficient of friction. That mu can be used to make predictions. That's what you're going to do in the skateboard lab, is you're going to calculate mu using your force of friction and your force of gravity, and then you're going to use it to calculate my force of friction from my force of gravity. You can be static or kinetic, as we talked about on the previous page. It can be from rest or while it's in motion. Next page. If that seems kind of vague or esoteric, I want to go through an example that will hopefully make it more realistic. So this is Josiah's backpack. It has a force of gravity of 80 newtons. That should be acting down. And he tries to move that. I'm going to check the camera, make sure we're recording this. Yes. He tries to move that, and it takes him 60 newtons to move that over, just to get it going. So just to get it going, the key there, that's our static friction to get it over that hump of the fact that it wasn't moving. So you write mu static, and I'm going to check and see if we can see that again. We can't. Okay. I'm going to move the camera a bit. Sorry, I hope this isn't so serious. Okay. So mu static equals force of friction over force of gravity. That's the same formula that was on the previous slide that we were looking at. And force of friction was 60 newtons. Force of gravity was 80 newtons. That calculates to 0.75. It's kind of the rare exception in science that it does not have any units on it, actually. Once again, it's a rating of how much friction is there. That's a pretty high rating overall if it took 60 newtons to pull an 80 newton object. Okay, moving on. Mu of sliding, so now he's pulling it across the carpet, and it now only takes him 45 newtons to keep it going as he's pulling it. So 45 newtons of friction. It still has that same mass of 80 newtons, or the weight of 80 newtons rather, sorry. 45 divided by 80 gives you 0.56. So it makes sense that sliding, which is a form of kinetic friction. These are both kinetic. They're sliding or they're rolling, they're in motion. Kinetic friction should always be the same or less, usually less than our static friction. Okay, next up is, let's use a different color. Next up is our rolling friction. So as Gates' invention is to put some wheels on that. Mu rolling equals force of friction over force of gravity. That is 4 newtons to make it roll, divided by 80 newtons still as our force of gravity. That comes out to 0.05 newtons as the force of friction when it's rolling. Notice that number is really tiny compared to these other numbers. That tells you there's very little friction or resistance when something's rolling compared to when something's sliding or to just get something moving. And now the last question has to do with the making predictions part. Store this in your brain, 0.05 for rolling friction. We erase this. So now the idea is he's added an extra 30 newtons to his backpack. So now his force of gravity is equal to 80 newtons plus 30 newtons, which equals 110 newtons. I should probably space that out a bit. 110 newtons. We set that same formula up. Mu rolling equals force of friction over force of gravity. The key being here, we have a new force of gravity. We know the mu rolling because we calculated that, and now we need to predict how much force is it going to require to pull that. So I'm going to put that in right there. The 0.05, which you're now taking out of your brain because you stored it there earlier, goes right there. 0.05 is equal to force of friction over 110 newtons. And this is hopefully easy algebra for you. Multiply both sides by 110 newtons by 110 newtons, and that cancels out. Force of friction is equal to 110 times 0.05. That should give you, I believe, 5.5 newtons of force. So once again, what we've seen is that it required 4 newtons of force for him to pull it when it was rolling. And then he added a 30 Newton textbook. It only took him an extra 1.5 newtons, which gives you an idea of what it means to be rolling or to have a really low coefficient of friction. You can add extra mass, it doesn't make it that much harder to actually pull there. Okay, so I went pretty quick with that. The general idea is if you know 2 variables, you can solve for a third, and these things right here, mu, once you calculate them, they should stay constant. The last thing I had people do, and you could do this at home. Oh, actually, let me go through this really quick, actually. So, thing I wanted to point out here, these are some real life things. I was making up all those random numbers on the previous examples. Steel on steel has a coefficient of friction of 0.74. Once it's sliding, it only takes 0.57. Glass is the highest one I have on this table. I specifically want you to look at rubber tires on a wet versus a dry road. The coefficient of friction on a dry road is much higher, and on a wet road it's decently lower, lower by almost 30% of that. And what that really tells you is, that's not 30%, never mind, forget what I said. What that tells you is that it's going to require either more force to stop when you're on a wet road because you don't have as much friction between the tires and the road, or same amount of force but applied over a longer period, which means you need to have a greater stopping distance with a car when you are trying to slam on the brakes and it's wet out. Also want to point out Teflon. Teflon is a non-stick surface. It's like that black stuff that you find in the bottom of your non-stick pans. It makes sense that that has an extremely low coefficient of friction, 0.04, because stuff does not stick to it very well. It's pretty smooth. Okay, what we did for the rest of the hour, I had people calculate their coefficients of friction, so you have to find the force of gravity of this is from that activity we did last week with the blocks. You have to grab your block. I'll be back. Okay, so you guys were pulling this block around on different surfaces, measuring how much force it took. That was the FF, the force of friction. That should really be lowercase there. You need to know the force of gravity if you want to calculate the coefficient of friction. So what you need to do is you need to suspend this mass here, and suspend your block as well, and read how many newtons that is. So if I bring this up to the camera, hopefully, maybe you can see that. No, it's really hard for you to read those numbers on there. You can maybe see that that's right around 6-ish, 5.8 maybe. Newtons is for a 500 gram block, or mass plus the block. And what you would do, I think I said 5.8, right? 5.8 newtons. So now you would take this, 0.6 divided by 5.8. In theory, that should give you a number right around 0.1. This one is 4.5. That should give you a number in my head somewhere right around 75% or so, 80%. We'll call it 0.80. I'm estimating those. What that's telling you is that the coefficient of friction between carpet and sandpaper is about 0.8. These are made up numbers, remember. Some people were actually getting numbers that were greater than 1. And what that just tells you is how much friction is there between those surfaces. If that number is greater than 1, it actually means that there's more force required to push the object than to pick it up, to work against gravity, which is kind of crazy to think about. Okay, the last thing I had people do was to watch that skateboarding video so we can do that lab tomorrow. So please make sure you've done that before you come to class. Please also note that the homework, which is right up here, is due Wednesday. That's when we are going to talk about Newton's laws. Thanks a lot. Have a great day.